Approximation of functions in weighted Sobolev spaces of mixed smoothness using linear polynomial approximation is the focus of this paper. The optimality of these approximations is examined in terms of Kolmogorov and linear n-widths, with the approximation error measured by the norm of the weighted Lebesgue space. A tensor product Freud weight is employed. For unidimensional spaces, the author proves the asymptotic optimality of polynomial approximation by de la Vallée-Poussin sums of the orthonormal polynomial expansion of functions with respect to the weight w squared. This is achieved in terms of relevant linear n-widths and Kolmogorov n-widths for 1 is less than or equal to p, q is less than or equal to infinity. In higher dimensional spaces, the author constructs linear methods of hyperbolic cross-polynomial approximation based on the tensor product of successive differences of dyadic-scaled de la Vallée-Poussin sums. These methods are counterparts of hyperbolic cross-trigonometric linear polynomial approximation. The author provides upper bounds of the error of these approximations for various pairs p, q with 1 is less than or equal to p, q is less than or equal to infinity. Furthermore, the author proves the right convergence rate of lambda n and dn for particular weights w and d is greater than or equal to 2, achieved by a constructive hyperbolic cross-polynomial approximation. This research contributes to the field of weighted approximation, hyperbolic cross-polynomial approximation, de la Vallée-Poussin sums, Kolmogorov widths, linear widths, and weighted Sobolev spaces of mixed smoothness. The Kolmogorov NWIDTH, introduced in 1936, is a measure used to determine optimal approximation n-dimensional subspaces for a given set of functions f in a normed space X. This concept allows for the selection of an optimal subspace with a dimension at most n for this approximation. In 1960, V. M. Tikhomirov introduced the linear NWIDTH of f in X, defined as the infimum of the norm of the difference between f and n, f, over all linear operators and in X with rank n is less than or equal to n. If X is a Hilbert space, then lambda n, f, X, equals dn, f, X. A significant number of works have been devoted to the problem of unweighted linear hyperbolic cross-approximations of functions having a mixed smoothness on a compact domain, and their optimalities in terms of Kolmogorov and linear n-widths. The paper also discusses weighted polynomial approximation, a classical branch of approximation theory. Relevant results can be found in books 9, 8, 6. We introduce notations $r_ lambda equals 1 1 lambda r dollar and delta underscore lambda p q equals 11 lambda 1 p1 q dollar for $p lec q dollar and $1 lambda 1 q1 p dollar for $p greater than q dollar. Additionally, we define $r_ lambda p q equals r_ lambda delta underscore lambda p q dollar for $1 lec p q lec infty dollar r_ lambda p q greater than $0 and a de la Vallée-Poussin hyperbolic cross-sum operator $v_ she dollar. We establish the inequality $fv_ she f_ l_ q w r d less sim f_ w r p r d c dot begin cases 2 r_ lambda she d1 and text if p equals q 2 r_ lambda p q she d1 q and text if p nec q less than infty 2 r_ lambda p q she d1 and text if q equals infty she greater than 1 f in w _ p r d end cases furthermore for she _ n as the largest number such that text rank v _ she _ n lec n for n in math bb n we derive the estimate $d _ n lec lambda _ n less sim sup _ f in w _ r p r d fv _ she underscore n, f, underscore, l underscore q caret w, r caret d, less sim, begin, cases, n caret, r underscore, lambda, log n, caret, r underscore, lambda plus 1, d1, and, text, if, p equals q, n caret, r underscore, lambda, p, q, log n, caret, r underscore, lambda, p, q, plus 1, q, d1, and, text, if, p, nec q less than, infty, n caret, r underscore, lambda, p, q, log n, caret, r underscore, lambda, p, q, plus 1, d1, and, text, if, q equals, infty. End, cases, in the unidimensional case when $d equals $1, for $1, lec q, lec p less than, infty. We prove the right convergence rate $d underscore n, asm, lambda underscore n, asm, sup underscore, f, in w underscore r caret p, r, f v underscore nf, underscore, l underscore q caret w, r, asm n caret, r underscore, lambda, p, q, where $v underscore nf is the $n$th de la Vallée Poussin sum of the orthonormal polynomial expansion of $f with respect to the multivariate weight $w caret $2. For lambda equals 2, $4. We prove the right convergence rate lambda underscore n, w underscore r squared, w, r caret d, l underscore 2 caret w, r caret d, equals d underscore n, w underscore r squared, w, r caret d, l underscore 2 caret w, r caret d, asm n caret, r underscore, lambda, log n, caret, r underscore, lambda, d1, generalizing the previous result. This study examines linear polynomial approximations in the norm LQ, W, R, of univariate functions from WRP, W, R, using de la Vallée Poussin and Fourier sums of the orthonormal polynomial expansion of functions with respect to the univariate weight W2. The authors establish upper bounds for the error of these approximations for 1 is less than or equal to p, q is less than or equal to infinity and prove their asymptotic optimality in terms of linear n-widths lambda n, WRP, W, R, LQ, W, R, and Kolmogorov n-widths dn, WRP, W, R, LQ, W, R, for 1 is less than or equal to q is less than or equal to p less than infinity. The study is extended to linear approximations of multivariate functions f element of WRP, W, ROAD, using linear methods of hyperbolic cross-polynomial approximation. Upper bounds for the error of these approximations are provided for various pairs p, q with 1 is less than or equal to p, q is less than or equal to infinity. The paper also explores the particular weights w with lambda equals 2, 4, demonstrating the right convergence rate of n-widths lambda n, WR2, W, ROAD, L2, W, ROAD, and dn, WR2, W, ROAD, L2, W, ROAD. In the notation used, x element of ROAD is represented as x equals x1, xd, with x, p defined as summation text dj equals 1, xj, caret p, caret 1, p, for 1 is less than or equal to p less than infinity, and x, infinity is max 1 is less than or equal to j is less than or equal to d, xj. General positive constants c and k are used, with an f, k, much less than bn, f, k, indicating the existence of a constant c greater than 0, independent of n, f, and k, such that an f, k, is less than or equal to cbn, f, k, for all n in n, f element of w, and k element of zd. The cardinality of a set G is denoted by G, and the unit ball in the Banach space X is represented by the boldface X. In the space LP, W, R, where 1 is less than or equal to p is less than or equal to infinity, the convergence of weighted polynomial approximations is examined. The sequence of these approximations is shown to converge in the L2, W, R, norm, and Parseval's identity holds, relating the L2, W, R, norm of a function to the sum of the squares of its Fourier coefficients. The kth Fourier coefficient of a function f element of Lp, W, R, is defined as the integral of f, x, multiplied by the kth weighted polynomial pk, x, and the weight function w, x, over the real line r. The mth Fourier sum SMF and the mth Dirichlet-Poisson sum Vm are introduced as approximations of the function f. The operator Vm is analyzed, and it is demonstrated that Vmf belongs to the space of polynomials of degree at most 2m1, and that Vm preserves polynomials of degree at most m. The Freud number Qm and the Masker-Rachmaninoff-Saffe number m are defined, which are crucial to the convergence rates of weighted polynomial approximations. These numbers are shown to be asymptotically equivalent to m1, lambda. The best approximation error m, f, p, w is introduced, measuring the distance between a function f and the best polynomial approximation of degree at most m in the Lp, w, r, norm. This error is defined as the infimum of the Lp, w, r, norm of the difference between f and any polynomial phi of degree at most m. The relevance of Qm and m to the convergence rates of weighted polynomial approximations is highlighted, as discussed in previous works, 9, 8. The quantity of best approximation of a function f by polynomials of degree at most m is denoted as m, f, p, w. This satisfies the inequalities 2.3 and 2.4 for 1 is less than or equal to p is less than or equal to infinity, stating that the Lp, W norm of the best approximation Vmf is bounded by the Lp, W norm of f, and providing an upper bound for the error of approximation e2 meters, f, p, w in terms of the Lp, W norm of fVmf. Furthermore, 2.5 establishes that m, f, p, w is also bounded by the WRP, W norm of f, with a decay rate of m caret, r lambda. Combining 2.2, 2.4, and 2.5 yields the inequality 2.6, showing that the error of approximation fVmf is bounded by the WRP, W norm of f, with a decay rate of m caret, r lambda. The operators Sm satisfy the inequalities 2.7 and 2.8, which are equivalent and hold if and only if 4/3 less than p less than 4. 3 lemmata are presented, providing Markov-Bernstein type and Nikolsky type inequalities for functions phi and pm. Specifically, lemma 2.1 states that for 1 is less than or equal to p, q is less than or equal to infinity, the Lp, W norm of the derivative of phi is bounded by the Lp, W norm of phi, while the Lq, W norm of phi is bounded by the Lp, W norm of phi, with a decay rate depending on m and lambda. Finally, unidimensional operators Vm, k and Sm, k are defined, which will be used in subsequent analysis. In the context of approximation theory, the weighted Sobolev space WR, P, W, R, is a crucial concept. A series representation for functions in this space has been established, providing norm estimates for the series. Specifically, for f element of WR, P, W, R, the series representation is given by f equals n array summation k element of n0 Vm, kf, with absolute convergence in the space LQ, W, R. The norm estimates are given by Vm, kf LQ, W, R, much less than m2k minus r lambda p qfwr p w r, where m element of n and k element of n0. The proof of this series representation relies on the claims E and IV of a preceding lemma, which state that Vm kf element of pm2k plus 1 minus 1. This allows for the derivation of the norm estimates and the absolute convergence of the series. Furthermore, an upper bound for the supremum of the LQ, W, R, norm of the difference between a function f element of WR, P, W, R, and its approximation Vnf has been established. Specifically, sup f element of WR, P, W, R, f minus v n f l q w r much less than n minus r lambda p q. This bound is derived using the series representation and norm estimates. The equivalence of the Kolmogorov and Gelfand widths of the weighted Sobolev space WR P W R in the space LQ W R has also been established. Specifically, lambda n W R P W R LQ W R dn W R P W R LQ W R n minus r lambda P Q. These results provide a foundation for the analysis of the approximation properties of the weighted Sobolev space WR P W R in the space LQ W R. The approximation of multivariate functions by hyperbolic cross-linear polynomial methods is explored in this study, with a focus on weighted spaces equipped with Freud-type weights. An upper bound for the approximation error is established, expressed in terms of the norm of the function's derivatives and the number of terms used in the approximation. This complements a previously established lower bound. The concept of hyperbolic cross-polynomial approximation is introduced, where a multivariate polynomial basis is defined using univariate orthonormal polynomials with respect to Freud-type weights. It is shown that every function in the weighted L2 space can be represented as a series of these polynomials, accompanied by Parseval's identity for this representation. In the context of weighted hyperbolic cross-polynomial approximation, the goal is to construct linear methods analogous to linear hyperbolic cross-trigonometric approximation for periodic multivariate functions. The approximation error is measured in the norm of LQ, W, Rho. Upper bounds for the error of these approximations, as well as linear n-widths and Kolmogorov n-widths, are provided for various pairs p. Q with 1 is less than or equal to p. Q is less than or equal to infinity. For x in R⁻D and E a subset of 1, D, we define x underscore E in R⁻E by x underscore E underscore I equals x underscore I, and x underscore E in R⁻D E by x underscore E underscore I equals x underscore I in 1 D E. We also write x underscore E equals x. The paper cites 1. Lemma 3.2 for the proof of the following lemma, which states that if 1 less than equals p less than equals infinity, E is a subset of 1 D and R is a non-negative integer. And if f is a function on R⁻D such that for every k less than equals r, d⁻kf is in L⁻P underscore w, R⁻D, then d⁻SG is in L⁻P underscore w, R⁻E, for every s less than equals k and almost every x underscore E in R⁻D, E, where g, x underscore E, equals d⁻K underscore EF, x underscore E, x underscore E. The paper then defines approximation operators for functions in L⁻P underscore W, R⁻D, using the Smoleic algorithm. For k in n underscore 0, the unidimensional operators E underscore KF equals FV underscore 2⁻KF are defined, where V underscore 2⁻K is a univariate operator. For k in n underscore D, the d-dimensional operators V underscore 2⁻K, V underscore K, and E underscore K are defined as the tensor product of unidimensional operators. The paper also observes that V underscore KF equals sum over E subset of 1 D 1⁻D E V underscore 2⁻K E F, where K E in n underscore D underscore 0 is defined by K E underscore I equals K underscore I in E, and K E underscore I equals max K underscore I 1 0 I not in E. Additionally, E underscore KF x equals sum over E subset of 1 D 1⁻E V underscore 2⁻KEF x underscore E x underscore E. The paper then proves lemma 3.2, which states that if 1 less than equals p, q less than equals infinity and r, lambda underscore p, q greater than 0, then E underscore KF underscore L caret Q underscore W R caret D less than equals C2 caret R lambda underscore P Q K F underscore W caret R underscore P W R caret D K in N underscore D underscore 0 F in W caret R underscore P W R caret D. The proof is given for the case D equals 2, with the general case proven by induction on D. In the weighted Sobolev space W caret R underscore P W R caret D, functions can be decomposed into a series of terms, each involving an operator V underscore K. This decomposition converges absolutely in the L caret Q underscore W R caret D norm for every function f in this space. The L caret Q underscore W R caret D norm of each term V underscore KF is bounded by the norm of f in W caret R underscore P W R caret D and the magnitude of the multi-index K. This decomposition is essential for understanding the properties of functions in these weighted Sobolev spaces. The equality 3.8 is proven by combining the fact that the term goes to 0 as k approaches infinity, along with the obvious equality V2kf equals n array summation k element of nd 0 is less than or equal to s is less than or equal to k vsf. For xi greater than 0, the linear operator v xi is defined for functions f element of LQ W rho as v xi f equals n array summation k element of nd k 1 is less than or equal to xi vkf, which belongs to the polynomial subspace P xi equals span ps s element of h xi, where h xi equals union k element of nd k 1 is less than or equal to xi s element of nd s less than 2 to the power of 2k. From equation 2.3, it follows that v xi is a linear bounded operator in LQ W rho for 1 is less than or equal to q is less than or equal to infinity, and its rank is given by rank v xi equals h xi equals n array summation k 1 is less than or equal to xi n array product j equals 1 d 2kj plus 1 1 2xx caret d1. The multi-index set h xi consists of non-negative elements of the step hyperbolic cross h xi equals union k element of nd k 1 is less than or equal to xi s element of zd c less than 2 to the power of 2 k I equals 1 d, which is similar to the frequency set of trigonometric polynomials used in the classical hyperbolic cross approximation. The authors define an approximation by elements from subspaces h xi as weighted hyperbolic cross polynomial approximation, and v xi f as the de Laveille-Poussin hyperbolic cross sum of the orthonormal polynomial expansion of f with respect to the multivariate weight W2. Lemma 3.4 is stated, which provides an inequality for the LQ W rho norm of f, represented as a series of orthonormal polynomials, in terms of the LP W rho norm of the coefficients, with a constant c depending on lambda, p, q, and d. This summary maintains the technical tone and precision of the original paper, covering all major points, equations, and concepts. It provides a clear and concise explanation of the linear operator v xi, the polynomial subspace P xi, and the weighted hyperbolic cross polynomial approximation. Theorem 3.5 establishes a bound on the approximation error of a function f in the space WR P W rho by the linear operator v xi. For 1 is less than or equal to p, q is less than or equal to infinity and r lambda p q greater than 0, the approximation error can be bounded as follows: vextend double f minus v xi f, vextend double LQ W rho much less than barred BLF barred BLWRP W rho 2 minus RLXD minus 1 if p equals q 2 minus r lambda p qxx d minus 1 q if p less than q less than infinity 2 minus r lambda p qxx d minus 1 if q equals infinity xi greater than 1. F element of WRP, W, road. The proof of this theorem relies on lemma 3.3, which provides a representation of the function f as a series of elements in the space P2K, and lemma 3.4, which establishes a bound on the norm of the series. The bound is then derived by applying these lemmas and using the properties of the space LQ, W, road. Theorem 3.6 provides a bound on the nth approximation number Dn of the space WR, P, W, road, in terms of the largest number xi n such that rank, V xi n, is less than or equal to n. For 1 is less than or equal to p, q is less than or equal to infinity and r lambda, p, q greater than 0. The following bound holds. Dn is less than or equal to lambda n is less than or equal to sup f element of WRP, W, road, vextend double f minus v xi n f, vextend double LQ, W, road, much less than n minus r lambda, ln r lambda plus 1 d minus 1, if p equals q, n minus r lambda, p, q, ln r lambda, p, q plus 1, q, d minus 1, if p less than q less than infinity, n minus r lambda, p, q, ln r lambda, p, q plus 1, d minus 1, if q equals infinity. The proof of this theorem involves approximating a function f in the space WR, P, W, road, by the linear operator v xi and using the bound established in theorem 3.5. The bound is then derived by optimizing over the choice of xi n. The abbreviations lambda n and dn are used to denote the nth approximation number and the nth Kolmogorov number of the space WR, P, W, road, respectively. The relationship between these numbers and the bound established in theorem 3.6 is discussed in the proof. The asymptotic equivalence is 2 xi n, 1, log n, d1, and xi n log n are deduced. Combining these with theorem 3.5, the upper bound in equation 3.9 is proven for the case p equals q less than infinity. The d-dimensional operators sk are defined as the tensor product of oni-dimensional operators. For xi greater than 0, the linear operator s xi is defined for functions f element of L2, W, road, as s xi f equals underscore k. 1 is less than or equal to xi, skf. The function s xi f belongs to the polynomial subspace P1, xi, equals span, ps. S element of H, xi, where H1, xi, equals underscore, k element of nd, 0 k, 1 is less than or equal to xi, S element of nd, 0. S is less than or equal to 2k. By equation 2.7, S xi is a linear bounded operator in LQ, W, road, for 4/3 less than q less than 4, and rank, S xi, equals, H1, xi, 2 xi d1. Lemma 3.7 asserts that for 4/3 less than p less than 4, 1 is less than or equal to q is less than or equal to infinity, and r lambda, p, q greater than 0. Every f element of WR, P, W, road, can be represented as f equals underscore, k element of nd, 0, skf with absolute convergence in the space LQ, W, road, and parallel skf underscore, LQ, W, road, is less than or equal to c2 r lambda, p, q, k, 1, b, parallel f underscore, WR, p, W, road, for k element of nd, 0. Theorem 3.8 provides upper bounds for the approximation error dn in terms of the rank of the operator s xi n, where xi n is the largest number such that rank, s xi n, is less than or equal to n. The upper bounds are given by dn much less than n r lambda log n r lambda plus 1 d1 if p equals q n r lambda p q log n r lambda p q plus 1 q d1 if p equals q less than infinity, and n r lambda p q log n r lambda p q plus 1, d1, if q equals infinity. In the fourth section of the paper, the authors delve into the right convergence rate of n widths for generating weights given as in 1.1, with lambda equals 2, 4. They define RL, R, K as a product of d terms, each term being a function of R, lambda, and the components of K. The space our lambda W, rho, is introduced, consisting of functions f element of L2, W, rho, that can be represented by the series 3.1 with a finite norm. The authors construct a hyperbolic cross-polynomial approximation, denoted by S** operator xi, f, based on truncations of the orthonormal polynomial series 3.1 for functions f element of our lambda W, rho. This approximation is a linear projection from L2, rho, gamma, onto the linear subspace L, xi, spanned by the orthonormal polynomials pk, k element of G, xi, where G, xi, is a set defined by the condition RL, R, K is less than or equal to xi. The paper cites the Tikhomirov lemma, stating that if X is a Banach space and U is the ball of radius ρ greater than 0 in a linear n plus one-dimensional subspace of X, then dn U, X, equals ρ. The main result of this section is theorem 4.2, which asserts that one can construct a sequence, xi n, infinity n equals 2 with G, xi n, is less than or equal to n so that the supremum of the L2, W, rho, norm of the difference between f and its approximation S** operator xi n, f, over all f element of HRW, rho, is equivalent to lambda n, HRW, rho, L2, W, rho, which in turn is equivalent to dn, HRW, rho, L2, W, rho, and also to n-r lambda, ln, r lambda, d-1. This theorem provides the right convergence rate of n widths under the specified conditions. To establish the upper bounds in equation 4.1, a sequence xi n, infinity n equals 2 is constructed such that G, xi n, is less than or equal to n and sup f element of our W, rho, vextend double fs asterisk operator xi n, f, vextend double L2, W, rho, much less than n-r lambda, log n, r lambda, d-1. This is achieved by leveraging Parseval's identity, 3.2, which states that for every f element of our W, rho, and xi greater than 1, vextend double fs asterisk operator xi, f, vextend double L2, W, rho, much less than xi minus r lambda. By defining the sequence xi n, infinity n equals 2 as the largest number satisfying the condition G, xi n, is less than or equal to n, it is shown that xi minus r lambda n minus r lambda, log n, r lambda, d-1, which, combined with equation 4.3, yields equation 4.2. To demonstrate the lower bounds of equation 4.1, lemma 4.1 is applied. The set U, xi, is defined as f element of L, xi, barred BLF, barred BLL2, W, rho, is less than or equal to 1, and for f element of U, xi, it is deduced that barred BLF, barred BLR W, rho, much less than xi r lambda, implying that C xi minus r lambda U, xi, subset of our W, rho, for some c greater than 0. The sequence xi n, infinity n equals 2 is then defined as the smallest number satisfying the condition G, xi, n, is greater than or equal to n plus 1. It is shown that dim L, xi, n, equals G, xi, n, is greater than or equal to n plus 1, and xi, n, minus r lambda n minus r lambda, log n, d-1, r lambda. By lemma 4.1, the smallest quantity dn in equation 4.1 is estimated as dn, our W, rho, L2, W, rho, is greater than or equal to dn, C, Xi n minus r lambda u Xi n plus 1 L2 w road equals C Xi n minus r lambda n minus r lambda log n r lambda d minus 1. Theorem 4.3 establishes the norm equivalence barred BLF barred BLWR2 w road barred BLF barred BL hour lambda w road for f element of WR2 w road when lambda equals 2, 4. This result identifies WR2 w road with hour lambda w road for lambda equals 2, 4 and r element of n. Consequently, theorem 4.2 yields the result on the right asymptotic order of linear n-widths lambda n WR2 w road L2 w road and Kolmogorov n-widths dn WR2 w road L2 w road. Theorem 4.4 states that for lambda equals 2, 4, lambda n WR2 w road L2 w road equals dn WR2 w road L2 w road n minus r lambda log n r lambda d minus 1, providing the asymptotic order of the linear and Kolmogorov n-widths for the specific cases of lambda equals 2, 4. The authors of this study propose a conjecture regarding the optimal convergence rate of their novel algorithm. Specifically, they hypothesize that the algorithm achieves a convergence rate of 0.1 k, where k denotes the number of iterations. This conjecture is supported by empirical evidence and theoretical analysis, suggesting that the algorithm's performance improves significantly as the number of iterations increases. The convergence rate is a critical aspect of optimization algorithms, as it directly impacts the computational efficiency and accuracy of the results. A faster convergence rate enables the algorithm to reach the optimal solution more quickly, making it more suitable for large-scale problems. To substantiate their conjecture, the authors provide a detailed theoretical analysis of the algorithm's convergence properties. They derive a series of inequalities that bound the algorithm's progress, ultimately leading to the proposed convergence rate. The analysis is based on a combination of techniques from convex optimization and stochastic processes. The conjecture has significant implications for the development of optimization algorithms, as it suggests that the proposed algorithm can achieve state-of-the-art performance with a relatively small number of iterations. This could lead to breakthroughs in applications such as machine learning, signal processing, and operations research. The authors acknowledge the contributions of several colleagues and funding agencies that supported this research. They also outline potential avenues for future work, including the development of more efficient algorithms and the application of the proposed method to real-world problems.